Hello, my name is Deborah Woods, and I will be talking about TESS Asteroid observations, detection processing pipeline results. I'd like to start by thanking my collaborators on this project. This is most definitely a team effort, and I'd like to gratefully acknowledge all of their contributions. An outline of my talk is as follows. I will be discussing the background and motivation for the linear TESS program. I'll give an overview of our asteroid detection software. I will discuss data features and data processing techniques, provide some asteroid detection results, and a summary. So first, TESS in context as an asteroid search sensor, the linear TESS program, as we call it. Linear is a Lincoln Near-Earth Asteroid Research, which is a heritage program at Lincoln Laboratory for asteroid detection. So we recognize TESS full-frame images as a very valuable resource for asteroid detection. Shown on the left is the sky coverage for TESS during year 3, July 2020 to June 2021. This looks similar for year 1. So TESS has very good coverage in the southern hemisphere during that time. Shown on the right is the sky coverage for all major asteroid search sensors for that same time period during year 3. As you can see, coverage in the southern hemisphere is most definitely lacking. And while the TESS images for the 10 cm aperture telescope don't go as deep as the major asteroid survey programs, they provide very complementary sky coverage. It is, of course, also useful when it's looking in the northern hemisphere, potentially places that the other surveys may not be looking. So TESS has a role in sky coverage, and this was recognized by the Planetary Defense Coordination Office, who funds the asteroid search sensor programs for all the major asteroid surveys. So in order to have a useful asteroid search sensor, what do we need for it? Well, the detection and discovery of asteroids, particularly near-Earth objects and potentially hazardous objects, requires highly accurate astrometry. We're looking for moving objects. We need to know exactly where they are, preferably less than 2 arcsecond residuals, which is less than 1/10 of 1 pixel for the TESS sensor. We need clean image subtraction for sensitivity to faint objects. Our tracker algorithm needs to be able to link detections and reject artifacts to work with very low SNR detections if we want to be as complete as possible. We need a low false alarm rate. So our expertise in this area comes from the linear program, Lincoln Near-Earth Asteroid Research. Lincoln Laboratory has been running asteroid search programs since the late 90s. Shown in the image on the upper right is the Space Surveillance Telescope. This is a 3.5 meter telescope. And on the lower right, GEODS telescopes, since they're 1 meter telescopes, part of the legacy linear programs. So our group has a lot of experience with asteroid search sensors, but the TESS data set provides a really unique opportunity and has some unique features being a space-based sensor. So the steps of our asteroid detection pipeline are listed here. I won't have time to go over each one of them in detail, but there is more information in a recent publication. I'll provide a reference in just a moment for that. But I'm going to highlight just a few of these steps that I think will be interesting to talk about today. The first is the measurement of the object centroid. So the TESS camera, it's wide field of view camera. It has a very compact PSF, and this was shown to be beneficial for photometry and for detection of transit signals. But it is challenging for astrometry where our goal is accurate positions. So the row on top in a linear scale shows the TESS PSF at different field angles. The bottom is a log scale to bring out faint features. And as you can see at large field angles, the PSF is asymmetric. And it's also undersampled relative to Nyquist. And so the centroid measurement can be challenging and the method of measurement is important. So we did some analysis to explore how to get the most accurate position measurements from the TESS images. We tested 3 different centroid measurements. 2 of them are taken from source extractor, the X and Y positions and the X and Y windowed positions. And the third is our own fit using a 2D Gaussian. So when you have a mostly symmetric PSF, the method is not terribly critical. The differences between them are about 1 arcsecond. So that's a little bit more than a 20th of the pixel. However, when you have a more asymmetric PSF, larger field angle, the differences between different methods can be quite substantial, more than a pixel in some cases. So the method of centroiding has a substantial impact on the measurement of the image center. So the centroid is just one step of the astrometry. The other is the astrometric plate solution. So we use the method outlined by Andras Paul, which is described in detail in this paper listed here. That method is 3 steps. The first is a mnemonic or tangential projection of the reference catalog centered on the optical axis of each catalog. We use the Gaia DR2 reference catalog, and this step is done for each camera for each sector once. The second step is the application of the optical distortion correction using a Brown-Conn rating model. And this was calculated by Andras during commissioning, and we use those same coefficients at all times. It's found to be very stable. The third step is a 5th order polynomial fit to the remaining uncorrected distortion. And this is calculated for each frame of each CCD. So any uncorrected distortion or changes in distortion over time due to variations in temperature or other small effects will be taken out on a frame-by-frame basis. And the details of this process are described in these references here. Now, we put together our centroid measurement with our astrometric solution, and we can compare our measured positions to catalog positions. So we're doing this test using bright stars and using the same method to measure the centroid as we use for our reference stars when doing our astrometric solution. We can compare the residuals for each of the different methods. So I'll note that it's very important when applying the astrometric solution to use the same method to measure the centroid to generate the solution and to measure the data. Because if you take a solution that was developed using one method of image centroiding and you apply it to your data when you have a different method, there will be biases, particularly at larger field angles. So we find that the 2D Gaussian fit provides the most accurate technique for centroiding the bright stars, and the fitted astrometry is quite good, shown here in the blue line. So what was shown before was our test for stars. If we compare the astrometric residuals for asteroid observations, for which the Minor Planet Center provided the evaluation of the quality of the astrometry compared to the predicted positions of known objects, we have over 800,000 observations of asteroids, and we compare our measured position with the reported truth data from the Minor Planet Center. So shown in the box and whiskers plot, the red line is the median at each field angle. The extent of the box, so the 25th and 75th percentiles, and the whiskers show the 5th and 95th percentiles. So what you can see is that our median is below 2 arc seconds out to all field angles, and 75th percentiles below 3 arc seconds for the most part. But what's most interesting about this is that the astrometric residuals are not a strong function of field angle. In other words, we are able to get an accurate astrometric solution all the way out to the corners of the field. Now, at the corners of the field, the optical distortion is up to 47 pixels. Correcting for that, and then also using our centroid measurement techniques, we are getting better than 1/10 of a pixel across the entire field. So this is really helpful in order to make use of the wide area coverage of the TESS images for our asteroid detection. Now, we note that the astrometric residuals are a strong function of magnitude. This makes sense because the faint objects are really pushing the detection threshold. The signal to noise is much lower. And so we have random centroid errors for the fainter objects. And this is not a problem because we have many detections for those tracks, but we can show that the errors are random and uncorrelated, and just a function of the ability to centroid a very faint, noisy, a very faint source that's nearly buried in the SNR. So another piece of our pipeline I'd like to mention is the difference image generation step. On the left is just a cutout from an original calibrated image. In the middle is the original minus the median image. And so subtracting the median removes things that are stationary leaving behind the moving objects. However, you can see a lot of artifacts here. These are from stars that are not fully subtracted, and I'll describe in a minute what's causing that. But when we take our original -R median and divide by clipped standard deviation, we are able to suppress those stellar artifacts because the standard deviation at the locations of those artifacts is going to be higher. So when we divide by it, we've reduced those. And the result shown on the right is a very clean image subtraction. Now, what's causing those artifacts? It's not the TESS system. The TESS cameras are operating beautifully, but there is a fundamental property caused by differential velocity aberration. So differential velocity aberration is a relativistic effect that arises from the relative pointing of the TESS camera and the motion of the spacecraft. And because of this, the apparent angle of the incoming light is shifted and the stars appear to shift slightly on the focal plane. And so these apparent shifts on the focal plane show up as small variations in stellar position. So when we subtract our median, it doesn't perfectly subtract at all times. The differential velocity aberration, or DVA, is a strong function of field angle and the satellite motion. So during close to perigee, DVA is much stronger, and at times further from perigee, it is less apparent. So in the top row, we're looking at a subtracted image near perigee, and at the bottom row at a different time. And these are the same CCD, same position, camera 1, CCD 3, sector 5, just at different times in the orbit. So just understanding where DVA is coming from and what its effect looks like, that helps us to mitigate it. But it can't be entirely removed because it's different across the field. So it's a function of field angle, therefore it can't be subtracted from all places at all times simultaneously. In order to understand the effect of DVA, we look at the change in DVA over time, or the time derivative of the DVA. This is from a memo by Lockwood from 2013, applying this prescription here. This allows us to predict and understand the strength of the DVA at different times. So what matters is how much has the DVA changed. If DVA was constant and the stellar positions remained exactly as they were, not changing over time, they would just subtract off cleanly in the median. But because they're changing, that's what matters. So we want to know how much is it changing. So we're looking at the time derivative of the DVA, shown in units of millipixels per hour, and this is computed for spacecraft ephemeris data and field angles for sector 10. I'll note that TESS doesn't record science data directly at perigee. That's when it is communicating with Earth to download the data. So we're not actually trying to take measurements here, but we are, just before and after perigee. So what do our predictions show? Well, if we look at if we take the TESS pixel response function that is predicted and at a certain field angle, and then look at the predicted PSF for the very slight shift in the current field angle as a result of DVA, and we do the subtraction of those, we can see what is the, where did the flux move to, so that when it is subtracted, what is left behind. So what's shown in these two panels is the same field angle, but slightly different subpixel centrations. And for a reference flux of 15,400 counts for a 10th magnitude star, the residual uncorrected flux after subtracting where that star has shifted in 8 hours, which is what we use in our pipeline, we can see that the residual flux is actually equivalent to a 16th magnitude star, which is well above the limiting magnitude of the TESS asteroid processing pipeline. So that's why we are seeing flux remaining from these stars when they have shifted slightly due to differential velocity aberration. So this is just one of the small challenges that we need to work with. Again, it's not a feature of the TESS camera. It is a relativistic effect, and it is just inherent in working with this kind of space-based data. So another step of our pipeline is to apply a field flattening algorithm to improve the image uniformity. Again, our goal is the detection of very faint sources. So we need as clean a background image as possible so that what is left behind are only the interesting moving objects and not artifacts. So we've applied a field flattening algorithm. Shown on the left is the original, shown on the right is the after applying the algorithm. And the details of the algorithm are in our recent publication that was referenced earlier. So how are we able to detect point sources in this cleanly subtracted image? Well, we're using a source extractor, and we have selected parameters that push it really as far as possible into the noise. So we are doing object detection on those cleanly subtracted frames, and we are setting our thresholds extremely low. And this, we recognize, will generate a lot of artifacts in these detections as well as real detections. But our tracker algorithm is able to handle that. And that's why we're able to push to such faint SNR. So how does our tracker algorithm work? Well, track generation is another important step of our pipeline. We start with all detections in frame 1. These are represented by the yellow stars. We then form candidate lines of track. That means we identify within a defined search radius. We look for any other detections within that radius in frame 2. And the radius is defined by a velocity constraint. So we have these yellow stars in frame 1. We look for anything within our search radius in frame 2, and identified candidate there. So we extend the candidate lines of track to subsequent frames. And we look for any detections that follow that path. And from this, in each subsequent frame, we are able to identify tracks that have at least m detections within n tracks. This algorithm is extremely efficient, and it is very good at rejecting clutter. So this allows us to push to very faint detection thresholds, because even though there's clutter in our detections, the clutter doesn't pass through the tracker. This approach is similar to what's presented in Kubica et al. 2007 for the intra-night linking of detections. So we find this method to be very powerful. As you can see, here's an example where we've detected a faint source moving through our background subtracted image. We have clean image subtraction, and the tracker is able to link potential detections among many possible trajectories. We have also robust false alarm filtering to exclude false detections. Some of our criteria for false alarm filtering, we reject anything that remains nearly stationary from frame to frame. We reject points that don't follow a piecewise linear curve to RA versus MJD or deck versus MJD. The second order polynomial is necessary because the tracks can appear slightly curved on the timescale of the 24 hours in which we're using our detections. We use the magnitudes. We reject points with the magnitude outside the moving window. And the moving window is necessary because we don't want to throw away asteroids that have actual variations in brightness, as you'll hear about in other talks today. We reject tracks on CCD columns, and this set of criteria and our tracker has been very reliable. We are finding that less than 0.2% of all tracks that pass our false alarm filtering are actually artifacts. So it's a very low false alarm rate. When looking at the characteristics of our tracks, we look at the number of tracks with certain numbers of observations per track. We have up to several hundred observations per track. The way our tracker algorithms run, we give it 24 hours of data plus or minus 3 hours on either side. And then in a later step, we link night to night for different tracks observed on different nights. Excuse me, for the same track observed on different nights. So the time span of these tracks from a couple hours all the way up to 300 hours. So we can have a very long view of an individual object. And you'll probably see some other talks studying individual objects where there's just a really great data set for those. So what are we observing? There is a spatial density plot of our asteroid observations. This is a plot of all moving objects observed by TESS in years 1 and 2. So these are individual observations. You can see, for example, certain objects moving through a field. So these have shown all points measured for each object. The spatial density plot has a color scale of log 10 per bin at a bin resolution of about 0.84 degrees. As you can see, there is a higher density of objects near the ecliptic plane and fewer at the poles. Certain sectors show a higher density than others, and we have found that tracks well with the stray light situation. So slightly higher stray light means a higher background, and when there's no stray light, we can't push quite as faint. And so the times with the lowest stray light are going to be the times with the largest number of detections because we're pushing fainter. Now, if we look at it as a distribution in ecliptic latitude, this shows a histogram of, again, all observations of all asteroids during years 1 and 2. It peaks near the plane, of course, but does not go to 0 at the poles. We're finding things all the way out to the poles. So this just illustrates, again, the utility of using the TESS data, this really wide field of view coverage. So for our program, we are interested, of course, in finding the moving objects. I know a lot of people using TESS data are interested in looking at, for example, light curves of stars, and asteroids interfering with those light curves would be a problem. So our pipeline, basically as a byproduct, allows us to identify where are the asteroids at all points in time, and we can compare that to the positions of the stars of interest from catalog, and we can identify where there is basically an asteroid passing too close to a TESS target star. If the asteroid passes within the aperture of the TESS target star, there will be a momentarily increase in brightness, as shown in these examples. However, if the asteroid passes through the background pixels of a target star, then the background will be temporarily over-subtracted, and it will result in an apparent transit. So future work for us is to publish the identification information for catalog stars with the time periods and pixel locations of asteroids that are interfering, because there are cases also where multiple asteroids are interfering in a single sector. So you could have 2 apparent transits that are actually just due to asteroids. And so when TESS moves to observe the ecliptic, this is going to be even more common. So I think it will be important to pay attention when measuring light curves of stars to make sure that the observed feature is not due to the passing of an asteroid, because this can throw off the detections both as increases and decreases in brightness. So these will be important to pay attention to, particularly coming up when it's observing near the ecliptic. So just want to show also some interesting images. We've detected comets for researchers who are interested in comet analysis. We have lists of, again, the location, pixel location and times of comets passing through TESS data. And this, I hope, will be a valuable resource for the analysis. Some really interesting plumes you can see as they're shifting a little bit over time. So I think there's some really valuable data here for that as well. So in summary, our linear TESS pipeline has been detecting moving objects and TESS full-frame images. We've observed over 19 million observations of 55,000 unique objects, which we've submitted to the Minor Planet Center for inclusion in their catalog. Included in those are 4,000 tracks of roughly 800 unique objects that don't match to the known objects. So these are candidates for discovery. This includes both asteroids, comets, near-Earth objects. And so we are waiting for the Minor Planet Center to evaluate those tracks and provide the ruling on candidate discoveries. Future improvements to the pipeline include new methods for multi-frame processing for faint streak detection, so we can push to even fainter objects in the TESS frames. Thank you very much for your time.